Okay, Chapter 7, Section 4 is all about determining chemical formulas, and more specifically, empirical formulas and molecular formulas. And the last bit we're going to ask you is, well, first we're going to ask you to determine them, and then be able to tell us the relationship between them and why it's so important. To start off with empirical formula, just for knowledge, empirical comes from our essentially means experimental. Alright, so your empirical formula is coming from your experiment. And what the empirical formula tells you is it tells you in one compound the smallest whole number mole ratio of the atoms in that compound. So one compound, what's the smallest ratio of the atoms in that compound? The molecular formula we're going to get to later. However, we'd like you to see it. Looking at this picture here, here is a water molecule. One oxygen bound to two hydrogens. The molecular formula there is two hydrogens, one oxygen. The nice part about water is it has the same empirical formula. That's the lowest whole number ratio of atoms. However, when you come to hydrogen peroxide, you have two oxygens and two hydrogens, all bound together in one molecule. So the molecular formula is H2O2, but when you look at the ratio of atoms of each element, it's for every one H, there's one O. So even though the molecule is four atoms bound together, the empirical formula just tells you the ratio of atoms in the compound. Ethane is another example here. Two carbons bound to six hydrogens, but the empirical formula just tells you for every carbon there's six hydrogens. It doesn't tell you what the molecule looks like. Why does that matter? Here we have two different compounds, two different molecular formulas. Put an M there and an M here. But when you break it down, they have the exact same ratio of carbons to hydrogen. So they have the exact same empirical formula. Now, you might do an experiment where you get the empirical formula as CH, which means for every one carbon, there's one hydrogen. However, that experiment isn't going to tell you if it's C2H2 or C6H6. And let me tell you what that means is you have two different compounds which have very different properties. And that's going to be a big issue. You need to know what compound you're working with so you know which properties you're going off of. To really get into empirical formulas, molecular formulas, you need to make sure you have an idea of percent composition because we're building off of percent composition. Here's a review problem. Go back to that if you need to. Okay, so once you have percent composition down, you can then go ahead and use that to calculate empirical formulas. So you do an experiment, you get the percent composition of each element in a compound, and we're going to turn that into figuring out the smallest ratio of the atoms for each element in that compound. Your book does this. This is on page 246, and your book does a nice job of setting out a plan for you. Okay, you're going to start with percent composition. You're going to turn that into mass composition. We're then going to turn that into moles or convert that to moles, and then we're going to use those moles to find the smallest whole number ratio. Okay? Here's a nice little trick they show you. If I pretend I have a sample of 100 grams, and I know 32.38% of that is sodium, then I know I have 32.38 grams of sodium. Now, it does not matter if I started with 100 or not. The idea, though, is it's a ratio. So regardless of the amount that I start with, if I keep the percentages the same, when I get down to the mole ratio of atoms, it will be the same. This is just an easy starting point with simple math. So what I want to do now, percent composition to mass composition, turn each one of these percents into a mass, and then I'm going to take that mass and I'm going to convert it into moles. I'm going to do that by using an old trick that we have from the periodic table. So I start with my 32.38 grams sodium, and I go ahead and hop on the periodic table and I say 1 mole of sodium is equal to 22.99 grams sodium. Do that math, multiply across the top, divide the bottom, so I end up with 32.38 divided by 22.99, and I get 1.408 moles sodium. I'm going to do the same thing with sulfur and oxygen. If you want to press pause and try it yourself to make sure you can do it, good idea. 22.65 grams sulfur. Okay, 1 mole sulfur gives me 32.07 grams sulfur. Cancel out my grams, do my division, and I end up with 0.7063 moles sulfur. And then oxygen, I've got 44.99 grams oxygen. Okay, 1 mole oxygen is 16.00 grams oxygen, and that will give me 2.812 mole oxygen. Notice each one of these I have 4 significant figures, so in my result of each division and multiplication I end up with 4 significant figures. Alright, the next step here, so I've got composition into moles. Now I want to find the mole ratio. Because basically, it doesn't do me much good to say 1.408 moles of sodium to 0.706 moles of sulfur, and so on. I want to find whole numbers so I can write them out in a chemical formula. So here's what I want to do. Nice little trick. If I divide by the lowest, let me get some pen color real quick. If I divide by the lowest amount, okay, well, divide this by itself. Give me a point, give me a decimal, here we go. Okay, pen doesn't want to work for a second. So we get this pen back. Okay, divide by itself, 7063. That will give me 1 mole sulfur. That's a whole number. So let's divide sodium by that. So those of you saying, why am I doing this? It's just a trick to try and get into whole numbers. Okay? If I divide 1.408 by 0.706, I end up with 1.993 moles sodium. Now that's not a whole number either. However, we're going to start this right now. If it's 1.9 and it's nice and close, we're going to allow you to turn that into 2 moles sodium. Okay? And same thing here. That gives me 3.981 moles oxygen, which I'm then going to round up to 4 moles oxygen. Alright, so there, I have whole numbers. I have 2 moles of sodium for 1 mole of sulfur for 1 mole of oxygen. And we all know 1 mole of anything is 6.022 times 10 to the 23 atoms. And so I can take these moles and directly convert them to atom ratios, where I can write my empirical formula. So if I have a compound with this percent composition, I know that the ratio of atoms in that compound is 2 sodium to 1 sulfur to 4 oxygen. And that gives me my empirical formula, my ratio of atoms. If that one was pretty easy for you and it makes sense to you, press pause. Try this. Okay. This one here, we've got a 60-gram sample of tetraethyl lead. Don't be thrown off by the 60 grams. Because remember our steps. We went from percent to mass. So if we start with mass, we already know how much mass of each element is in the total. We don't need to go to a percent. So we can start right here with our numbers. And again, we're trying to find the empirical formula. So just like before, I'm going to go ahead and start off with 38.43 grams of lead, which is Pb. I'm going to do this one without the table for us. All right. 1 mole of lead. All right. From my periodic table, 1 mole of lead is 207.2 grams lead. Okay, get rid of my grams, and that calculation will give me 0.1855 moles lead. Alright, finish it up for carbon and hydrogen. 17.83 grams carbon. That's multiplication. 1 mole carbon is 12.01 grams carbon. Cancel out my grams. Get 1.485 moles carbon. Hydrogen's fun because we know that hydrogen is a 1-to-1. So, 1 mole hydrogen is 1.00 grams hydrogen. No calculator needed here. 4 moles hydrogen. Now I want to point out something. In this example, you have the most lead, but the least amount of atoms, or as it says here, the least amount of moles, which is the least amount of atoms. So don't always think that the one with the highest mass is going to have the highest amount of atoms. It doesn't always work that way. I'm going to change colors real quick to show the next step. Okay, so here I've got my lowest number of atoms. Divide that by itself. Okay, and that gives me 1 mole lead. And divide carbon here. And that will give me, that's 8.005, which I'm going to round to 8. That's close enough. Mole carbon, and my hydrogen. And that's going to give me 20.16, which I'm going to round to 20 moles hydrogen. So I've got 20 mole hydrogen, 8 mole carbon, and 1 mole lead. So I know my empirical formula when I'm looking at atoms ratios is 1 lead for every 8 carbon for every 20 hydrogen. And that, my friends, is your empirical formula, which shows the ratio of atoms in a compound. Alright, so that is empirical formulas. Now, if you remember our picture, the molecular formula is not always the same thing as the empirical formula. The molecular formula actually tells you the formation of the compound and the amount of atoms needed for 1 molecule. Now I want to put that in your notes. Molecular formula gives you 1 molecule. This right here is just another example to drive that nail that something with an empirical formula of this can be multiple different compounds. And we don't want that. We want to know the molecular formula of what we're working with so we can know the properties. A couple notes for this one. You want to go ahead and put down X times the empirical formula will give you the molecular formula. So if you did what we just did and found the empirical formula, you can then find this whole number ratio to find the molecular formula. I'm going to go back and show you that picture again. So here's our empirical formula, right? I find that whole number, and if I multiply the empirical by the whole number, which is our x in that previous slide, that will give me my molecular formula. So that's how, when I go from empirical formula, I find my empirical formula, I can then convert it to my molecular formula. Now, I've got one equal sign, one unknown, two unknowns. I need another equation. For all you math whizzes, you know that. Two unknowns needs two equations. So I come down here, and I also can rely that the formula masses maintain the same relationship. And the first trick I'm going to show you is I'm going to show you how to go from empirical formula to formula mass. We're going to work off sample problem M here, which is in your book. And in sample problem M, the only reason I want to show it to you really is first we're going to use it, but also if you look at their work, they find a mole ratio that comes from 1 mole of phosphorus to 2.497 moles of oxygen. That doesn't really give us a whole number. Alright? So a trick here is that is not the lowest whole number ratio, but to find it, I know if I multiply each side by 2, that will give me an empirical formula of P2O5, because 2.497 times 2 is just about 5. And that gives me my empirical formula. So sometimes when you divide by the lowest, it doesn't give you a close enough number to round. So you have to do one more step of math to make sure you get the lowest ratio possible. Okay, so using from sample problem M, the empirical formula is found to be P2O5. So I told you the first trick I'm going to tell you to go is empirical formula to empirical formula mass. The easiest way of doing this is, you know you have 2 moles phosphorus and 5 moles oxygen. Okay? You also know the AMU of phosphorus and oxygen. So if I have 2 moles of phosphorus, I'm going to multiply that by phosphorus AMU, which is 30.97 AMU. Okay? And oxygen, I know it to be 16.00 AMU. Grab those from the periodic table. So I know in my empirical formula, 2 moles of oxygen, if I multiply that by the AMU, or excuse me, 2 moles of phosphorus and multiply that by the AMU, I'm going to get 61.94 AMU here, and then 80 AMU here. And if I add those together, I'm basically adding 2 moles phosphorus to 2 moles oxygen. What I have here, I'm going to get 141.94 AMU, and that's going to give me my empirical formula mass. Okay. Another nice trick we have is we know the molar mass of the compound to be 283.89 grams per mole. Well, I'm going to tell you right now, the molar mass can be directly related to the molecular formula mass. Because when I know the molecular formula, if I do the exact same calculations as I did over here, then I'm going to go ahead and get 283.89 grams per mole. So I can actually convert that number to 283.89 AMU, and I can plug in right here. So here's the equation I have. I've got x times empirical formula mass equals my molecular formula mass. I'm still trying to find my molecular formula. If I take this equation, work it around a little bit, X equals molecular divided by empirical that is going to give me my whole number that I can use to multiply against my empirical formula. Let's fill this in. So X equals 283.89 AMU divided by 141.94 AMU. Look at that, the AMU's cancel, which is nice. And I get X equals 2.005, which I can then go ahead and just say X equals 2. All right. So now I have my X value. I've got my empirical formula. I can find my molecular formula by coming down here and just doing 2 times P2O5. If I take that 2 and I distribute it through, that will give me a molecular formula of P4O10. And that gives me my molecule. Okay? One more time. If that sample was easy for you and you think you get it, try this one first. And then watch me do it and see if we match up. I'm going to go ahead and mark down what I'm looking for. Again, I'm looking for the molecular formula. Okay? I know the empirical formula, and I know the formula mass. Alright? And so remember, the first thing I'm going to do is I'm going to take this empirical formula and I'm going to turn it into empirical formula mass. Alright? I have nitrogen, 1, multiply that by the MU of nitrogen, which is 14.01 AMU. Alright, well, 1 times 14.01 gives me 14.01 AMU. And then I have 2 hydrogen, and I multiply that by AMU of hydrogen, and that gives me 2 AMU. Add those together, and I know my empirical formula mass is 16.01 AMU. Now remember, I have the equation X times empirical. I'm going to just abbreviate here. Formula mass equals molecular formula mass. Alright, so I've got my X equals empirical formula mass, which I have right here, and then I've got my molecular formula mass, which I've got in the problem. I do a little algebra, and I get my X equals molecular formula mass on top, 32.06, actually the decimal gets in there, AMU, and I divide that by 16.01 AMU, and I get an X that I can round up to 2. AMU's cancel out. So I know my factor I'm multiplying my empirical formula by is 2. Just to help you see it, we'll do it also. So X equals, now let's set up the whole thing. X times empirical formula equals molecular formula. All right, and I'll do my, I'll plug in here and we'll do the math from there. So I know my X is 2. My empirical formula is NH2. I go ahead and distribute my 2. And I go ahead and get a molecular formula of N2H2, which is, N2H4. Yeah, so N2H4. And that gives me the formula of my molecule, which is a different molecule from NH2. Remember, this is pages 245 to 249 in your text, and sort of wrapping up all of Chapter 7, or the last bit of Chapter 7 that we need. So go back through those pages and look at those sample problems if you need a little extra practice.